In the last video, I finished by generating 10 random double numbers between 0 and 1 using math.random. I asked the question, when would you use this instead of using the methods on the random class? Maybe you've found some code on the internet on how to randomize a character, and it comes back with code similar to what I am showing here. I'll talk about this code in a minute, but first, you should know that the math.random method uses an instance of the random class and invokes the next double method on that class. The first time you call math.random, a single new instance of java.util.random is created and used for all subsequent calls. I've done something a bit similar in code samples where I created a static field on a class for a random instance. In general, you'll probably use the random class, but you should recognize what this code is doing. Let's get back to the same project from the last video, the math.random project. The for loop I ended with simply printed out 10 randomly generated double numbers with values between 0 and 1, including 0 but less than 1. I can use this code with a multiplier of 10, which I'll do next. Running this, I get a list of numbers now greater than or equal to 0 and less than 10 still double numbers. I can cast these numbers to ints. I'll use a cast, so int in parentheses, and I'll wrap the rest of the expression in parentheses as well, so the cast will be applied to the entire expression. Running this code, you can see I get a list of integers now, from 0 up to and including 9. If I wanted numbers between 1 and 10, I'd just add 1 to that. This is looking very familiar to the code I showed you on the first slide. It's a commonly used way to get a range of numbers. This slide is a representation of the code I just walked through. The lower bound was 1 and upper is the exclusive bound, and in our case it was implied to be 11. This was a pattern used a lot because until JDK 17, the random.nextInt method only supported an upper bound. The lower bound was always assumed to be 0. In addition, when you use random, you have to use an instance of it either in place or using a variable set up previously. I've shown you examples of using random either as a variable instantiated in place in the expression or using a static final field on a class. Getting back to my code, I'll replace 10 with 26, and instead of adding 1, I'll add 65 as was shown on the first slide. Running this, I'll get a random number between 65 and 91. Why is this relevant? I'll change my println statement to a printf instead and add a formatted string literal as the first argument. I'll print the random number first as a number using the specifier %d and also using the positional identifier $1. I'll say that is equal to a character specifier %c and I'll use the same argument, so again $1 there. If I run this, I can see my random integers and the character each one represents. Now I'll do this same thing, but using a method on random. I'll first add a separation line here. Next I will create an instance of random. I'll copy that loop and paste a copy below. I'll remove the second argument to the printf altogether. Now I'll call nextInt on my random instance. I'll pass 65 as the lower inclusive bound. I'll make 91 the upper exclusive bound. This is 65 plus 26 letters in the English alphabet. I mentioned this before, but I'll repeat it here. This method, the overloaded version of nextInt that allows us to specify a range, was included on the random class in JDK 17. In that release, random was modified to implement the random generator interface. Overloaded versions of the nextInt, nextDouble and nextLong methods have default implementations on that interface. Running this code, I get a similar result to the previous code. I prefer to use the character values in cases like this. I think it helps to improve the readability a bit, so I'll copy lines 37 through 41 and paste that on line 43. I'll remove the duplicate declaration of the random R. I'll change 65, instead casting the character A to an int, and 91 to cast the character Z to an int and add 1. So the upper bound is 1 more than the Z character, again because this bound is exclusive. I will move the second argument to the next line so we can see it. If I run that, I'll once again get a character between a capital A or a capital Z. Using this code, I could very quickly change this to a different character range without having to look up the corresponding integers. I've covered quite a few of the methods on the random class already. You might remember I used next boolean in my student engagement code in the streams section. That takes no arguments, but returns a random boolean each time. I've shown you the two overloaded versions of nextInt. Passing one argument is passing an upper exclusive bound. Passing two arguments, you're passing an inclusive lower bound and an exclusive upper bound. There are similar versions of these for doubles, longs and floats. I haven't covered the no argument version of nextInt, so I'll show you an example of that next. I'll copy lines 43 through 47 and paste that copy just below on line 49. I'll first change my formatted text. I'll remove the equal sign and the code after that, except the %n. I'll also remove the arguments to nextInt. I'll just move that second argument back up to the previous line. Running this code, you can see that for this method I may get up to the full range of integers randomised, including negative integers. I can specify a negative lower bound, which I'm not sure I've shown you yet in the course. I'll pass -10 as the lower bound and make the upper bound 11, so I should get random numbers between -10 and 10. If I run that, I can see that my integers are limited to -10 as the lower bound and 10 as the highest number. Now that you've seen and used streams, I want to show you a couple of other methods on random that provide random streams. JDK8 added support to get streams of random numbers with methods on this class. I'll add another separator line in my code first. I'll use the random variable r here and call them method ints with no arguments. This returns an int stream. I'll limit the stream to 10 ints and terminate the stream with a for each that simply prints the int. If I run this, I get 10 random integers, both negative and positive, again bounded by the integers min value and max value. I can specify the lower and upper bound for this random stream as well. I'll copy lines 54 through 57 and paste a copy just below. I'll change the call to r.ints and pass 0 as the lower bound and 10 as the upper bound. If I run this, I'll now see 10 random ints somewhere between 0 and 9. There's one more version of this method. This one has 3 arguments. The second and third are the lower and upper bounds. The first parameter specifies the size of the stream, meaning a finite stream will be returned instead of an infinite stream. I'll copy lines 59 through 62 and paste that copy below. I'll add that first argument to the call r.ints, making it 10. I'll remove the limit intermediate operation because it's no longer needed. If I run that, I get similar results to the previous stream pipeline, so 10 numbers randomly generated between 0 and 9. I can also just pass a single argument to this method. It's important in this case, when passing just one argument, to remember this argument is specifying the stream size and not the upper bound. I'll copy lines 64 through 66 and paste that on 68. I'll remove the second and third arguments in the call to ints. Running this gives me 10 randomly generated ints, negative and positive. That's very different from an infinite random stream of ints from 0 to 10, if that's what you were expecting. There are also methods to get double streams and long streams with similar parameters. Finally, there's just one other thing I want to show you. You can instantiate a new instance of random with an overloaded constructor that takes a single argument. This argument is the seed. What's a seed? In most programming languages, the random functions aren't truly random. Algorithms exist that create distributions of numbers that achieve what a random distribution might look like over a large range of values. These are called pseudo-random number generators, and they're dependent on an initial value called a seed. Let's see what the API has to say about the two random constructors. I'll bring that page up. You can just look for the random class API, then select constructors. Here you can see the two constructors and the documentation for both. In the first case, for the noargs constructor, we're told that the seed of the random number generator is set to a value very likely to be distinct from any other invocation of this constructor. It doesn't say how it does that. In the second constructor, it accepts a long value called seed. That is the initial value of the internal state of the pseudo-random number generator and is maintained by the method next. If you like learning about software engineering, let me encourage you to do some reading on different pseudo-random number generators. For now, let's get back to the code and see what Java's really doing in that noargs constructor. I'll click on this constructor in my code on line 38. That brings up the random class at the constructor code, and you can see it's chaining a call to the constructor that takes a seed, passing a default value. It's using system.nanotime combined with some method called seed uniquifier, and that's actually listed just below this constructor. Notice the comment in this method. It's a reference to a journal article, so if you're the curious sort, make sure to check that out. For the rest of you, stay with me just another moment. I'll Control-click on that seed uniquifier reference there. And there is Java's first part of its seed equation. It's passing a literal long value to an atomic long wrapper class. The main takeaway here is that this number, along with the system's nanotime, is used to generate what Java calls a number very likely to be distinct. Why would we want to change it? For most randomization purposes you wouldn't, but it's helpful to know about this if you want to test code that uses a random number generator. Let me show you what I mean. First, I'll create a local variable, a long, and set that to the system.nanotime, which the Java code was using in part of its expression. This method returns the running JVM's high-resolution time source in nanoseconds. I'll use that as my seed and create a new instance of random I'll call pseudo-random. I'm going to copy lines 64 through 66, the code that generates 10 random ints as a stream that are between 0 and 10. I'll paste that on line 74. I'll change the variable name r to pseudo-random on line 75. Next, I'll change the code on line 76 from a method reference to print the numbers to a lambda so they're printed on a single line. I'll copy lines 73 through 76, pasting that copy on line 78. This time though, I want the pseudo-random variable to be called not really random, and I'll change that first on line 78, then on line 80. I'll also add a \n in the println statement, so it prints a new line first. In this code, I'm using the variable nanotime as the seed in both random instances. Because I'm using my variable, I'm seeding both instances with the exact same number if I run this code. You can see that I get the same set of numbers printed in both cases. If I rerun it, I'll get different numbers because nanotime's a different seed each time, but they'll be the same for these two instances of random. You can also use the setSeed method to do something similar. This is something to be aware of if you use the same seed for invocations of the random class. In the case of the random class's noargs constructor, it used that long value wrapped as an atomic long and the nanotime to make it highly likely that the seed used was unique for each invocation of the random class. You might use these methods to ensure that you get a predictable set of pseudo-randomized numbers, either for testing or maybe verification of some statistical model that's based on a random population. Okay, so I'll end the video here. In the next video, I'll be giving you a randomization challenge. See you in that next video.